We're going to talk about the second half of chapter 7 in your text. Remember that when we discussed the first half, I mentioned that in the new edition, which is where these slides come from, they've split this chapter into two. So this really isn't chapter 8 in your text. This is the second half of chapter 7. So in the beginning of chapter 7, we made it through the point where we understood how to draw something called Lewis dot structures, which are a very basic qualitative understanding of how to draw molecular structures. Now we're going to go, and then we also learned about formal charges. That's where we ended. And now we're going to go on to think about higher level theories that are more accurate. So and the first thing before we do that is just to talk about shapes. So when we drew Lewis dot structures, we never talked anything about what the shape of the molecule would look like. And so in order to understand shapes, we have to introduce a new theory called VSEPR, which stands for valence shell electron pair repulsion. So you're going to determine the shape, and the shape is going to be important because the shape will determine the properties of a bulk system. So the Lewis dot structure and then the shape of that molecule will determine what kind of interactions the molecules have. So things like their boiling point, what they look like as solids will all be determined by knowing their shapes. So this will be important. So to start out, if you want to understand the shape, you first just draw an electron dot structure for the molecule, and you count the number of electron charge clouds surrounding the atom of interest. You predict the geometric arrangement of charge clouds by assuming that the charge clouds are oriented in space as far away from one another as possible. So valence shell electron pair repulsion is a very, very easy concept. Electrons are all negatively charged. So they would like to have as much distance from other negatively charged particles as possible. So we're going to arrange all of the electrons, whether they're charged clouds that take part in bonding or lone pairs, in such a way to give them as much space as possible. So when we only have two charged clouds, so in this case, we're talking about the central atom. So carbon has two bonds. One of each of them is a double in carbon dioxide. But that's still just two different regions of space that we want to put electrons. And so the best way to, the best geometry is to have it 180 degrees so that those electrons around the carbon atom can be 180 degrees apart. So the lone pairs on the oxygen aren't going to determine the angle because they're not at the vertex of the angle. So hydrogen cyanide is similar. It has two charged clouds. One of them is a triple bond, one is a single bond, but it's still two regions of space that want to be as far apart as possible. So it's also going to be 180 degrees. If you have three charged clouds, you can have a couple different situations. So you can have carbon with three atoms hooked onto it, and that molecule is formaldehyde. That's the one we did the Lewis structure for, and I couldn't remember the name. So the angles are going to be about 120, because if you have three regions of space with electrons and you want to keep those as far apart as possible, if you put them at 120 degrees, they'll be as far apart as they can be. So you can also have three charged clouds where they're not all bonds. Some of them are lone pairs. So if you look at sulfur dioxide, it has a sulfur hooked on to two oxygens and then a lone pair. So that still, the angles want to be about 120, but we're going to call it bent instead of trigonal planar, because that lone pair helps describe the geometry, but it isn't part of the geometry. You don't tell where electrons are when you give the name of a structure shape. So four charged clouds ends up, it's a tetrahedral geometry. So the angles are about 109.5. And if you have three charged clouds in a perfect tetrahedral molecule with all four of those red atoms are atoms instead of lone pairs, the bond should be 109.5 exactly. But just like with three charged clouds, there are other ways to think about it. Methane has 4 charged clouds, and they're all atoms. The angles are 109.5. Ammonia has 3 charged clouds that are bonding and 1 that's a lone pair, but it still has a total of 4 charged clouds. And so it's going to be angles about 109.5. It's going to be a little bit less. It's going to be 107. And you can't know that exact angle with VSEPR theory, but you can know that it should be less, because as this picture demonstrates, when you have bonding electrons, they're very localized between the atoms, the nitrogen and hydrogen, but that green lobe shows that a lone pair is more diffuse. It's not so directed on a line, and so it takes up a little more space. And so the angles are going to be a little less than 109.5 because that lone pair needs a little more space. Water molecule is very similar, except now it has 2 lone pairs and 2 shared pairs. And when that happens, the angle should be about 109.5, and we'll call it bent because there are only 3 atoms. But those 2 lone pairs, just like the one above in ammonia, take even more space. And so the angle's even less than 107. It's going to be 104.5, which we'll talk about a theory where you could actually calculate that number. 5 charged clouds, you're going to have 3 in a plane, and they'll have angles of 120, and then 1 above and 1 below at 90. So this is the only one of your VSEPR geometries where all the angles aren't the same, but this will give all of the pairs of electrons as much space as they can have. So with 5 charged clouds, you can have the first situation, phosphorus pentachloride, and in that case, all the charged clouds are bonding pairs. And so the geometry ends up being trigonal bipyramidal. But if you replace one of those pairs with a lone pair, you end up with something that looks more like a seesaw. So you take off the fluorine that's in the plane, because when you think about it, if the lone pair needs a little more space, it would make most sense to remove one of the atoms that are in the plane where the angles are 120, because that gives it a little more space than the one above and below that's only 90 degrees from the other ones. So you're going to take off one of the fluorines when you draw this Lewis dot structure, so that that lone pair can be in the plane with the others that are 120 degrees apart. So these names will be in a table in a second, so we call this one seesaw. 5 charged clouds where 2 of them are lone pairs. Same thing as before, we want to take those off of the, take the fluorines off in the plane where they're 120 degrees apart. And when you do that, you end up with something that looks like a T. Oh, and the bottom one is where you have 3 lone pairs. With 3 lone pairs, it's going to make sense. All those lone pairs should be in the plane where they're 120 apart. That forces the 2 iodines that are hooked onto the central iodine 90 degrees from the central plane. And so you end up with a linear molecule when you have 3 lone pairs and 2 shared pairs. 6 makes a geometry where all the angles are 90. So in the plane, out of the plane, they're all the same. So when you look at that, we call it octahedral. And when we have one of those replaced with a lone pair, it's going to be called square pyramidal. And you could replace any one because they're all 90 degrees apart. If you take 2 off, the best thing will be to put the lone pairs opposite each other, because that gives them more space. If you put them adjacent to each other, those lone pairs that need more space would be not given as much as they could have. So here that shows you that this molecule, where you have 2 lone pairs, ends up being a very symmetrical molecule, because all the fluorines will be in the same plane and the 2 lone pairs will be above and below that plane. So you're going to get this table, which is just a summary of what we just talked about, on your test. So it goes up through all of the shapes that we've talked about. But I will give you this table. So if you can draw your Lewis structure, determine how many charged clouds you have, this table is super easy to use. So ending here, we have ended our basic qualitative approach to molecular structure, which is Lewis dot structures and then valence bond, or VSEPR, I'm sorry, valence shell electron pair repulsion. And in those theories, you wouldn't be able to get the exact geometry. We'll go through two more theories. Valence bond is a little better than valence or than Lewis dot structures and VSEPR, but then there'll be one that's the best, which is molecular orbital theory, which we'll talk about last. And you'll do a computer lab with that one so that it will make even more sense to you. So valence bond theory, it's a quantum mechanical model that shows how electron pairs are shared in a covalent bond. So this is just showing you that, well, it's actually better to start here with the description of what the theory is. Covalent bonds are formed by the overlap of atomic orbitals. So that's the big thing, is that valence bond theory, because if you think about it, we spent an entire chapter talking about the fact that electrons aren't dots. They have a probability of where we can find them. And so now we're gonna introduce those orbitals in as we talk about how bonds are formed. So covalent bonds within valence bond theory are formed by the overlap of atomic orbitals, each of which contains one electron of opposite spin. Each of the bonded atoms maintains its own atomic orbitals, but the electron pair in the overlapping orbitals is shared by both atoms. The greater the amount of overlap, the stronger the bond. And so when you look at how we think about it, if we have H2, the two s orbitals just come together and they can overlap. And that's how you would describe it in valence bond theory. You'd say that the bond within the H2 molecule is formed by the overlap of an s orbital on each hydrogen. Notice there's arrow up and arrow down. That means the electrons that are in those orbitals, there's one in each on each hydrogen. They have to have opposite spin in order for them to pair and then be in the same orbital. We call that type of bond a sigma bond. It's where if you cut it across the bond axis and look on it towards one of the nuclei, it's circular. So that's a new definition of the shape of the bond. Fluorine can also form a sigma bond, but now if you look at it, each fluorine has a 2p orbital with one electron. And if you take the two lobes that are the same color, remember that means they have the same sign, then when you push them together, you will get overall electron density in between the two fluorine nuclei. And so once again, if you were to cut that across the bond axis and look at one of the fluorines, it's circular, so it's also a sigma bond. And then you could have overlap of different types of orbitals on different atoms. So to make HCl, you can take the s orbital on hydrogen with an electron with spin up, and the p orbital on chlorine with an electron with a spin down. And if you take the two parts that have the same sign, when you push them together, you'll get overall electron density. And so you'll get a higher probability of finding electrons there, which makes it a stronger bond. And you'll get one up and one down. So they're paired within that bonding orbital. So we talked about this. Just take a second to reread this. So when you're talking about the atomic orbitals, it doesn't always work out so well to be able to explain the geometry. And so there are additions to this. One of them is something called hybridization. So first we'll talk about something that are called sp3 hybrid orbitals. So how can the bonding in methane, CH4, be explained? Carbon has 4 valence electrons and 2 unpaired electrons. So the carbon ground state electron configuration is a 1s2, 2s2, 2p2. And remember that the electrons that take part in bonding are the valence ones. So those 1s electrons won't be part of our discussion. But you look at that and you say, well, there aren't 4 orbitals on carbon that each have 1 electron in them. So something is wrong if we know that methane forms 4 bonds. And so we can think about it this way. So we start out with the ground state electron configuration on the left. And if you excite one of the electrons from 2s to 2p, you end up with 4 orbitals, each with 1 electron. The problem is that they're not equivalent orbitals. You have an s and 3 p's, and if you go back and look at VSEPR, let's go back real quick to VSEPR. Yeah, the first example they give you shows you for the tetrahedral shape is that methane should be tetrahedral. The angles should be 109.5. And when you look at these unequal orbitals, not are they unequal, you have p's and s's, but it's also true that even just the p's, they're 90 degrees from each other. So your bonds would be 90 degrees and they need to be 109.5. So what we're going to do is use a theory that says, okay, we're going to take the s orbital and the 3p orbitals, we're going to add them together. And when you do that mathematically, which we won't do, but trust that it works, you end up with 4 new orbitals. So we added 4 orbitals, we get 4 new ones. They're all 109.5 apart, and we call them sp3 hybrid orbitals because they have 1 part s and 3 parts p. Just so happens when you do, hope they don't show you the geometry. That's too bad. So we'll talk about the other kinds of hybrid orbitals. Yeah, then they'll show us the geometry. So another type of hybrid orbital is an sp2. So sp3 meant we added an s orbital and 3 p orbitals. Now if it's sp2, it means we're going to add an s and only 2 of the p orbitals. So we will come back and talk about this. They're not really giving you enough detail to make sense out of it, except that sp2 hybrid orbitals are 120 degrees apart. So if you form sp2 hybrids, the green lobes in the picture are the hybrid orbitals. And then remember, we only use 2 of the p orbitals. So there's a p orbital that has a pink lobe and a blue lobe that's perpendicular to that plane. So now if we look at some of the structures you can make, so methane then, because this is the example we talked about, methane could have a carbon that has sp3 hybrid orbitals. So that means it now has 4 equivalent orbitals at 109.5 degrees apart, each with 1 electron with the same spin, we'll say. And then if they're introduced to 4 hydrogen atoms, each with a 1s atomic orbital with an electron in it that has the spin the opposite way, the s orbitals on each hydrogen can overlap with 1 of those sp3 hybrid orbitals, and you can make single bonds between the carbon and each of those hydrogens. So this is the sp2 that they just showed you. And this one is how that might bond. So for sp2 hybrid orbitals, you want to think about this picture as showing how a carbon double bond would form. So if you have 2 carbon atoms, each with an sp2 set of hybrid orbitals, one of those sp2 orbitals on each carbon can come together. And on the right-hand side, that region in green in the middle shows you that that's the first bond that forms. That's a sigma bond. But then if you squish those together, above you get a pink lobe and below you get a blue lobe. And that's the second bond. That's what we'll call a pi bond, because if you cut it across the bond axis and look, it looks more like a dumbbell. So a double bond in carbon is 1 sigma bond formed by the overlap of an sp2 hybrid orbital on each carbon atom. And the pi bond is formed by the overlap of a p orbital on each of the carbon atoms. This is sp2 hybrid orbitals. And they end up being 180 apart. So it's the sum of 1s and 1p, which means when you look at the right, that means you have 2 sp hybrid orbitals now on this if it's carbon, and then you have 2 p orbitals left over. So a pink and a blue lobe twice perpendicular to each other shows you that if you make SPs, you only use one p orbital. So you have 2 more p orbitals left over on whatever atom you're talking about. And so if you want to think about how a triple bond is formed, and I'll show you a 3-dimensional model of this in class, you have those sp hybrid orbitals. And so if you squish the 2 atoms together, in the middle on the right, you see the green lobe, which is a head-on of those 2 sp orbitals, which forms a sigma bond. But then as you're pushing it together, the 2 p orbitals overlap, and you get 2 pi bonds, one from each overlap of 2 p orbitals, and those are pi bonds. So the important thing is, if you know the geometry, you know what hybrid orbitals you have. So if you draw a Lewis dot structure like we did with methane, and then figure out what the geometry is, you can just use this table, and you could put this on your note card to tell you what the hybrid orbitals must be. Okay, and this section of these slides we're going to skip and come back to when we do your chapter 10. So they start us thinking about how the properties of molecules determine the properties of solids and liquids, and we'll do that in a later chapter. Okay, and the last thing we'll do in your chapter 7 is molecular orbital theory. And we're going to do a whole computer lab on this, which I think will really help make this make more sense, because it's pretty abstract. So we take the idea that atoms have atomic orbitals, and you had to solve Schrödinger's equation to get those wave functions, which are orbitals. You could do the same thing for a whole molecule. So a molecular orbital is just a wave function whose square gives the probability of finding the electron within a given region of space in a molecule. So it's exactly the same as an atomic orbital, except that you've calculated it with Schrödinger's equation for a whole molecule. And so we can have sigma bonding, well, we can have sigma orbitals, and some can be bonding and some can be anti-bonding. And so if you add together 2 s orbitals, for example, you get what looks like an ellipse on the right-hand side at the top. And that's a bonding orbital, because if you look at it, there's a high probability of finding the electrons between the nuclei. If you look at the bottom of that, you could also add those 2 orbitals together by changing the sign of one of them. And when you do that, what happens is you get a pink and a blue lobe, so they have different colors, and that means they have different charges. They have different charges, that means when the function changes from pink to blue, it must have gone through 0. So that means it has a node. It has a region of space where you have 0 probability of finding the electron between the nucleus, and so between the nuclei, and so that means it's anti-bonding. The orbital on the top right-hand side helps hold the molecule together, and on the bottom right-hand side helps pull the molecule apart. So in order to figure out the bond order, you're going to count how many electrons are in bonding orbitals and subtract from that those that are in anti-bonding orbitals, divide by 2, because a bond is 2 electrons. And so we'll do some examples using that equation. And so when you've drawn, or when you've calculated these on the computer, what you'll find is that they'll have different energies. And in the central part of this slide, it's showing you that the bonding orbital has lower energy, so the electrons will go in there first, and then the anti-bonding orbital is much higher in energy. And so in this particular case where you're making the hydrogen molecule, just H2, you only have 2 electrons to put in. A molecular orbital can contain 2 electrons just like an atomic orbital. And so you have 2 electrons in a bonding orbital, 0 in the anti-bonding orbital, and if you divide that by 2, you end up with a bond order of 1. So molecular orbital theory is just confirming what we knew from Lewis dot structures, that the bond within a hydrogen molecule is a single bond. So if we think about a other types of molecules with the same molecular orbitals. So if you make H2 minus, the anion of the H2 molecule, you have to put one more electron in the picture. So now you would have put 2 in the bonding and 1 in the anti-bonding. So now if you take 2 minus 1, you get 1 divided by 2 should give you 1/2. So that's incorrect at the bottom. The bond order for H2 minus should be 1/2, not 2. So the numerator 2 minus 1 is 1, the denominator's 2. For helium, why doesn't helium form a diatomic molecule? Well, helium would have 4 electrons, 2 from each helium. You put 2 in bonding and 2 in anti-bonding. So the numerator is 2 minus 2, which is 0. And so the H2 molecule doesn't exist because there's no benefit to its energy to forming a bond. Another thing you can get from molecular orbital theory is whether or not the molecule should be magnetic or not. So if it's called diamagnetic, all electrons are spin paired. Diamagnetic substances are weakly repelled by magnetic fields, whereas something paramagnetic is what you think of as a magnet. And that happens when there's at least one unpaired electron. So paramagnetic substances are weakly attracted by magnetic fields. So oxygen is predicted to be diamagnetic by electron dot structures because they show you how we would have drawn it. We would have paired the electrons to form 2 bonds and then put 2 lone pairs on each oxygen. So both valence bond theory and electron dot structures would say that it should be diamagnetic. But in reality, it's known to be paramagnetic. And you can understand that by using, so if we use the diagram on the right, because it's for O2 and F2. So if I put in the electrons for O2, I'm going to put in 12 total electrons because each oxygen's valence will contribute 6. So the first electrons will go in the sigma 2s, and then 2 more in the sigma star 2s. So that's 4. And then 2 will go into the sigma 2p, and then 4 will go into the pi 2p. So that's 2, 4, 6, 8, 10. And now I have 2 more electrons to put in the picture. And notice if you go up to the first set of pi star, so the pi star 2p, which is anti-bonding, because those 2 orbitals have the same energy, 1 electron will go into each of those. That's Hund's rule. So we follow all the same rules with molecular orbitals as we did with atomic orbitals. And that means that it should be paramagnetic, that you have 2 electrons that are unpaired, which we couldn't understand from Lewis dot structures and valence bond theory. So molecular orbital theory is the best theory. The problem is you have to have a computer to create these diagrams. And so we'll learn how to make these diagrams and just think about what the computer's doing and when we do a lab together this week. Okay, so this is just showing you the shapes. So the shape of 2 p orbitals coming together, we can have the very top orbital, if they come together with pink on blue ends, we get a node, and that very top orbital would be called a sigma star because it's anti-bonding, because there's 0 probability of finding the electrons between the nuclei. And it's sigma because if you cut it across the bond axis and looked, it would be circular. You can also have sigma bonding that looks similar to the second one from the top. So if you have the 2 lobes overlap that are both pink, you'll have a high probability of finding the electrons between the nuclei, even though you also have those lobes on the outside that you have a probability. And then you can make pi orbitals. So the top 2 are sigma, the bottom 2 are pi. The very lowest one is a pi bonding. So if you slide together the 2 atoms on the left-hand side of the screen so that the 2 pink are on the top and the 2 blue are on the bottom, you'll end up with the very bottom pi 2p. And so that's going to be bonding, but it's going to be pi instead of sigma, because if you cut it across the bond axis and look, you have a lobe above and a lobe below, so it's not circular. And then pi star is going to have lobes above and lobes below, so that it's pi, and it's going to be star because if you slide the two p orbitals together by flipping one first, so you have blue on the top of one and pink on the top of the other, then when you slide them together, in order for it to go from positive to negative for the function, it has to go through 0. So you're going to have a node in between the nuclei, and a node helps pull the molecule apart because it doesn't have electron density between the atoms, helping hold it together. This just shows you how you fill them. So the example in the middle, O2, we did that one. Nitrogen, you'd put 10 electrons in, so you're always just going to put in the valence electrons. Then you can determine the bond order, and you can determine whether or not it's paramagnetic from filling a molecular orbital diagram. So there are combinations of valence bond theory and molecular orbital theory. You don't really have to worry about that. We'll just, at this point in your careers, learn the two theories separate of each other. So that should be it for your chapter 7. The next thing we're going to do is totally shift gears and start talking about the energy that's released or absorbed during a chemical reaction. So reactions like burning gasoline in your car, why does that give you energy so that you can move your car? After that, we'll talk about gases. And then after that, we'll talk about solids and liquids. And that is all of Chem 107. So we're at the end, essentially, of understanding the properties of elements, and then the shapes of molecules and the properties of molecules.